Okay, in the last class, we had finished discussing the frequency domain interpretation of continuous time signals and systems. Now, that's what you have studied in your previous class. The question is, what about the discrete time signals and systems? So we understand that discrete time signal and systems in time domain. So in discrete time signal and systems, we understand that the input-output relation is given by if you have a system xn and yn, then yn is simply xn convolution with the impulse response h of n. But we again ask ourselves the same question, which is that we understand the time domain operation of discrete time signals and systems. Is there a similar frequency domain interpretation to discrete time signal and systems like the one we studied for continuous time things? And the answer is yes, but to be able to answer that question of what is the frequency domain interpretation, we first need to understand the concept of frequencies in discrete time, which is a little different than in continuous time. So discrete time frequencies differ a little from the continuous time world. So heuristically, the meaning of frequency stays the same, which is it tells us something about the rate of change of a signal. So that stays the same, but there are some fundamental differences between continuous time frequencies and discrete time frequencies. So let's try to remind ourselves some key properties of continuous time frequencies. The first is that in continuous time, all frequencies are distinct. What's the meaning of that? If you have two signals, let's take the example of pure sinusoids. If I have two signals, cosine of omega 1t, and I have another signal which is cosine of omega 2t. Okay. And if I guarantee that omega 1 is not equal to omega 2, so you have two sinusoids, omega 1 and omega 2 are two different frequencies. If they are not the same, then what this means is that x1 of t is not equal to x2 of t. Okay. So distinct frequencies mean distinct signals. That's one key property which we'll see is not true in discrete time. The other property is that in continuous time, if omega 1 is bigger than omega 2, then this means that x1 t fluctuates or changes faster than x2 of t. Okay. So these two key properties are not the same in the case of discrete time frequencies. But the fundamental concept of sinusoids in discrete time stay the same. So in discrete time world, the fundamental, and I'm putting periodic in quotes because periodicity is not always true in the case of discrete time cosines. Are the same ones that we saw earlier for continuous time. It's cosine of little omega n Now, in the literature, to distinguish between continuous time and discrete time frequencies, sometimes what is done is that capital omega is used for continuous time frequencies. It's just a dummy variable, okay? But just to make that easier, capital omega is used as a notation for continuous time, and little omega is used as a notation for discrete time frequencies. You can have xn equal to sine of omega n, or you can have x of n equal to e to the j omega n. Okay, so very similar, but in discrete time, the little omega, this is its units are now units of frequency in discrete in continuous time are radians per second, but in discrete time there is no notion of second. The fundamental notion in discrete time is you have different sequence values, or the term that is used is sample. So the units in this will be radians per sample. Okay. So in continuous time, when we say the frequency is, let's say, 2000 pi radians per second, what it means is, if you are thinking of this complex sinusoid, it is going to turn around this unit circle 2000 pi. It's going to cover 2000 pi radians, so it's going to do 1000 rotations of this circle in 1 second. Okay? The notion of the rate in discrete time is it's just one sample. So what you are asking is from one sample to the next sample, how many radians it covers. Okay, how many radians is that thing going to cover? That's the notion of discrete time. Okay, if you're thinking of in terms of the unit circle in the complex exponential plane. You can give sometimes omega is written as 2 pi f, just like in the continuous time world, and in that case f, which is defined as omega over 2 pi, its units are used as cycles per sample. Again, you can't give it the name of hertz because it's not cycles per second, okay, which is the definition of hertz. It's cycles per sample, which means that how many cycles of this cosine are covered between one sample and the next sample. Okay, so the fundamental signals in the discrete time world are these cosine, sine, or e to the j omega n, which is related to sine and cosine. But there are key differences because of the reason that we are in the discrete world. So let's look at the first difference. Not all discrete time frequencies are distinct. Rather, given omega 1, omega 2 equal to omega 1 plus 2 pi k for any integer k, k is the same frequency as omega 1. Okay. So what does this mean? Let's say, and we'll work with complex sinusoid because that's easier to do analysis. Since cosine and sine can be expressed through complex sinusoids, the same analysis holds. So let's say we have some frequency x1 n equal to e to the j omega 1 n. Okay. So omega 1 could be, for example, 2 pi by 3. So it's a 2 pi by 3 radians per sample frequency. What this means is that between two samples, if you are on the unit circle, it covers 2 pi by 3 radians between two samples. Okay. So if I write this as e to the j omega 1 plus 2 pi k of n, where k is an integer. So the question is are they really equal? And we can write that as e to the j omega 1 n times e to the j 2 pi k n. Now what is this e to the j 2 pi k n? If it's as long as k times n is an integer, which is true because k is an integer and you are in discrete world, so n is an integer, right? Which is not true in the case of the continuous world because the variable there can take any value. It doesn't have to be an integer. But in the discrete world, since both of these are integer, the value of this is equal to 1. So what this means is that whether I have a frequency omega 1 or I add some multiple of 2 pi to that frequency, my signal looks exactly the same. Okay? In other words, I only have a certain range of frequencies in which my frequencies are distinct, and after that frequencies start repeating themselves. Or the discrete time frequencies are periodic with a period of 2 pi. The second difference is in terms of what happens to the frequencies as they go from lower to higher. So what happens to little omega as it goes from 0 to, let's say, 2 pi. As I said earlier, in continuous time, you keep on increasing the value of frequency and your signal start changing faster and faster. Okay. Now for that, we'll just use simple properties of the sinusoid. So let's take x1 of n equal to cosine of omega 1 and let's say that omega 1 is between 0 and pi. So it's only a number between 0 and pi. And let's take x2 of n equal to cosine of omega 2n with this condition that omega 2 is defined as 2 pi minus omega 1. So if omega 1 is between 0 and pi, so omega 2 is between pi and 2 pi then. Okay. So we have here the situation that omega 2 is bigger than omega 1. But if you look at x2 of n, that is equal to cosine of 2 pi n minus omega 1 n. That's just the definition of omega 2n. And if I use the Euler's identity, I get e to the j 2 pi n times e to the minus j omega 1 n plus e to the minus j 2 pi n times e to the j omega 1 n over 2. Now e to the j 2 pi n, you will see this again and again. If it's e to the j 2 pi times an integer, it is 1. And e to the minus j 2 pi n is also 1. So all I get is e to the j omega 1 n plus e to the minus j omega 1 n over 2, which is equal to cosine of omega 1 n. Okay. So what we are seeing is that even though my frequency omega 2 is bigger than omega 1, the sinusoid is exactly the same sinusoid with a frequency of little omega 1. So effectively what is happening is that if you look at the frequencies, okay, here is your 0, here is your pi, and this is your 2 pi. In discrete world, what happens is that as you go from 0 to pi, your frequencies are increasing, which means that if you plot your cosine of omega n as a stem plot, it will start wiggling faster and faster and faster. Okay? But once you cross pi, then every frequency in the region pi to 2 pi is actually just the same as the frequency of 2 pi minus omega 1. So a frequency here gets mapped actually to 0 around this region around pi. And a frequency here gets mapped here. So the frequency near 0 is a smaller frequency, but a frequency near 2 pi is also a smaller frequency. Okay? And the reason follows because of this periodic property of the discrete time frequency. So the first difference that I explained and this, they are related to each other. Okay? So what happens in the discrete time world is the fundamental if you want to really talk about frequencies. In the continuous world, you can talk about frequency of 1 kilohertz, 1 megahertz, 1 gigahertz, 1 terahertz, and you can keep on going. There is no stopping. Okay? You can keep on talking about higher and higher and higher frequencies. But in the discrete world, what happens is that the highest, I'm going to talk about positive frequencies right now. The highest frequency is actually little omega equal to pi. And by highest, what I mean is you can say that I have a frequency of 2 pi times 1 mega radians per sample. Okay? But that will just be equal to a frequency of 0 radians per sample. So the highest frequency that you have in the discrete world is omega equal to pi. The fundamental region that you should worry about is 0 to pi. If you try to increase the frequency any higher, the signal looks as if, so that if I took it near 2 pi as I showed here, the signal looks as if it was close to 0. So that is the fundamental difference from the continuous time world. You can talk about high frequencies, but the signal is not going to start changing any faster. Okay? So the fundamental frequencies are 0 to pi, and the terminology that is made is that all frequencies around the neighborhood of 0 and any 2 pi multiple of it, because we already saw in the first difference that frequencies are 2 pi periodic. So around the neighborhood of 0 plus 2 pi k are considered low frequencies. And all frequencies around the neighborhood of pi plus 2 pi k, where again k is any integer, are considered high frequencies. So in general, in the discrete time world, what happens is that when we are talking about frequencies, we divide our discrete time frequencies into chunks of 2 pi regions each. So if this is 0, let's say this is minus pi, pi, this is 3 pi, this is sorry, this is 2 pi, this is 3 pi, minus 2 pi, minus 3 pi. Okay. In discrete time frequencies, we often either focus only on frequencies 0 to 2 pi or minus pi to pi. The convention is that we only look at frequencies between this region. Why? Because if we know about frequencies between minus pi and pi, we know all the other frequencies, because all the other frequencies are exactly the same as the frequencies between minus pi and pi. And the other aspect is that discrete time frequencies effectively around 0, they are low frequencies. And not only around 0, but any integer multiple of 0. So it means around any frequency that is around 2 pi, which is around minus 2 pi. They are all low frequencies, and they are exactly the same. They are not different frequencies. And frequencies which are around the region of pi, okay, they are high frequencies. And again, any multiples of pi. So that's one of the key differences that you will see again and again when we talk about discrete time frequencies. So if you were to think of, for example, let's take a signal of xn equal to cosine of pi n, okay, which means that this has a frequency of pi radians per sample. Now, cosine of pi n, we know for n equal to 0, for any even n, right, what will xn be? For any even n, xn will be equal to 1. And for any odd n, xn will be equal to minus 1. Okay. So if you were to plot this, you will see at 0 you have 1, then minus 1, then 1, and minus 1. This is what it looks like. And this is the highest frequency. If you try to, this is the fastest that a signal can wiggle in the discrete world. Right? It's taking positive value in one sample and it takes the negative value in the next sample. But if there is nothing faster that you can do, because in the continuous world, between any 2 points, there are more points. So you can make the signal go faster in between those 2 points. But in the discrete world, because of this fact that you are stuck, there is nothing that exists between 0 and 1, that's the fastest you can do. Okay? If you were to think of, for example, xn equal to j pi n, right? What this means is that at one sample, it will be here. At the other sample, it will be here, right? So it will keep on fluctuating between the two, and effectively between any 2 samples, it covers pi radians. So the frequency here is pi radians per sample. If you think of it in terms of the unit circle, between any 2 samples, it basically covers pi radians, and it's keep on going down. But if you were to increase the frequency any bigger, if you were to say it's pi, something bigger than pi, then what's going to happen is your next sample will be here, but that is equivalent to going in the negative direction with these many radians. Okay, so you can think of it in different ways to understand the concept of discrete frequencies. It was important for us to understand the concept of discrete frequencies, because what we want to do is the same as we did in the continuous world, which is we argued that every signal in the continuous world can be thought of as made up of a large number of frequencies. Okay? Even if the signal is not periodic, we said it can be done. We want to do the same in the discrete world. So what we want to argue is that every finite energy signal in discrete time can be thought of as consisting of an infinite number of sinusoids. The sinusoids you can think of them as either cosine or sine or complex sinusoid e to the j omega n. That's what we will work with. So, this condition is exactly the same as the continuous time. The notion of finite energy is different. In continuous time, the notion of finite energy was that you take the integral of the absolute value squared and it is finite. In discrete world, what we want is that if I am given a sequence, then xn absolute value squared n from minus infinity to infinity is less than infinity. Okay, so that's how energy is defined in the discrete world. If this is true, then we want to argue that any signal can be written as combination of frequencies, and the expression that we get is very similar to the continuous time expression. So if you remember, what we had said was x of t is 1 over 2 pi minus infinity to infinity x of j omega e to the j omega t d omega, right? And what this meant was that it consists of an infinite number of frequencies. Their frequency is omega, and this is the amplitude and phase of the frequency, which we call the continuous time Fourier transform. We want to do the same for discrete time, so we get this. In the discrete world, we are using the frequencies as omega, little omega. So our frequencies are e to the j omega n. So we are saying our signal consists of, and d omega, of an infinite number of these discrete frequencies. What is the amplitude and phase of each frequency? We write that as x e to the j omega. Okay. This is very similar to this continuous time Fourier transform expression. The reason we write it as x e to the j omega is to make it clear that this is for the discrete world. Because remember, capital omega and little omega are just dummy variables. And we'll be doing examples where we'll be mixing continuous and discrete Fourier transform. So we really need to have a way of using different notation for the two. Okay, so you should really think of this as x of e to the j omega. It's nothing more than saying it's a function of little omega. Okay, e to the j is just there to distinguish it from the continuous time Fourier transform. Okay, so this is all good, but there is a key difference between the representation of the continuous time signal as summation of frequencies or infinite number of frequencies and the discrete time. And the difference is that in the discrete time world, the number of the frequencies that we have, if we know between, for example, minus pi to pi, or we know them between 0 to 2 pi or any 2 pi contiguous region, we know about all the frequencies. So the limit of integration doesn't go from minus infinity to infinity. It only goes from minus pi to pi or any other continuous 2 pi region. I could very easily have 2 pi here and 4 pi as the upper limit, but the convention is we write it as minus pi to pi. Okay, but any 2 pi region will suffice. So in the discrete world, our signals, just like the continuous world, can be written as consisting of an infinite number of frequencies, discrete time frequencies. And just like in the continuous world, x of e to the j omega, this is called discrete time Fourier transform. DTFT. Effectively, the amplitude of x of e to the j omega tells us about the magnitude of frequency little omega present in the signal. So say if I had x of e to the j pi by 3, if this was equal to 0 for any signal, then this means that xn does not contain omega equal to pi by 3 frequency. Similarly, the phase of x of e to the j omega tells us about the phase of frequency little omega present in xn. Okay. So the role that x of e to the j omega plays is exactly the same as x of j capital omega. It tells us about the magnitude and the frequencies. Now, how do we calculate x of e to the j omega? How do we calculate the discrete time Fourier transform? The formula is summation n equals to minus infinity to infinity x of n e to the minus j omega n. Okay. Since xn is a discrete time signal, we have summation. Otherwise, you can relate it to the continuous time Fourier transform. If you remember, x of j omega is minus infinity to infinity x of t e to the minus j omega t dt. Right? So if you compare, they are exactly the same. Instead of integration, you have the summation. Instead of continuous time sinusoid, you have discrete sinusoid e to the minus j omega n. Okay, so we can now write down, I can give you the equation of discrete time Fourier transform now, which is this. It is called the analysis equation. Why analysis? Because it tells us the frequencies that make up my signal. Okay, so it's the analysis equation because it helps us analyze the signal. The previous frequency, this version that I showed, this thing is called the synthesis equation because it tells us, if you know the discrete time Fourier transform, how do you synthesize your signal from that equation. Okay. So formula-wise, they are easy to understand. I just want you to make sure that you grasp the meaning of what the discrete time Fourier transform is telling you. It's exactly the same expression. It's telling you which frequencies are present. So let's look at the case. The notation that will be used is xn Fourier transform x of e to the j omega. I'll again repeat, there is nothing special about e to the j omega. This is just a notational convention to say that it's the discrete time Fourier transform. It's really a function of little omega. Okay? X of e to the j omega is defined above, and xn is defined as 1 over 2 pi minus pi to pi x of e to the j omega n d omega. Okay. Now, keep these few things in mind. Xn itself is discrete time. But the discrete time Fourier transform basically helps us understand that extent consists of an infinite number of frequencies. And the discrete time frequencies, while they are between minus pi and pi, if you know about that, you know everything. The frequencies themselves are continuous. Okay? So I can talk about 0.00001 pi frequency. I can talk about 0.00001 pi frequency. The frequencies, the discrete time frequencies themselves that arise from the discrete time Fourier transform are continuous. Okay. So the key thing to remember is that xe to the j omega itself is a continuous function of little omega. So even though the signal is discrete time, the discrete time Fourier transform is continuous in little omega, because in most discrete time signals, unless the signal itself was periodic, in most discrete time signals, you have to have an infinite number of frequencies to be able to reconstruct that signal. Okay? If a signal is aperiodic, if it's not periodic, you can't have just one or two frequencies, because those frequencies likely will have a periodic sinusoid associated with it. You can't reconstruct that original signal. So you often need an infinite number of frequencies. Now, just because of the fact, as we talked about, that discrete frequencies, as long as you know them between any 2 pi range, you know them all. Because of that very fact, the DTFT x of e to the j omega is also periodic in little omega with a period of 2 pi. So in general, DTFT is defined from little omega from minus infinity to infinity. But if you know any 2 pi regions of that, you know all the DTFT. Okay? And seeing that is easy, if I have x of e to the j omega, I can write it as x of e to the j omega plus 2 pi k, so any multiple of 2 pi. And I plug it into the definition of DTFT, which really shouldn't come as a surprise, because we have already seen that the only frequencies that matter are any contiguous 2 pi regions. So if I do that, I'll get n from minus infinity to infinity, x of n, e to the minus j omega n times e to the minus j 2 pi kn. But e to the minus j 2 pi kn, if k is an integer and n of course is an integer, then this is equal to 1. Right? So we are only left with this expression, which is equal to x of e to the j 2 pi, x of e to the j omega. So if I change my omega by a factor of 2 pi, I get back exactly the same thing. Okay. Now, I want to, before I give you examples, I just want to make sure that we are able to interpret the DTFT. DTFT is really telling us about the individual frequencies that make up my discrete time signal, and in particular, the magnitude of the frequency at a particular value tells us about the magnitude of that frequency, and the phase tells us about the phase of that. So let's say we ask the question how to interpret the DTFT. We'll try to look at the interpretation of the phases, but let's say this is the magnitude plot of my DTFT. So between minus pi and pi, I have something like this. Okay, and what And I want to make sure that you understand that after this, it will just repeat itself. So it's periodic, which means that after this, it will go back. It will repeat itself. This will be 2 pi, okay? And similarly here. And it will keep going. But we will focus only on the regions of minus pi and pi, because if we understand this region, we understand all the frequencies. So what is this amplitude plot telling us? It's saying that, for example, whatever was the value here, right? Let's assume that the value here was 3 pi by 4. Or maybe pi by 4 is a better option. Minus pi by 4. Okay? And this is, so what this means is that this signal, whichever signal corresponded to this DTFT, that signal has no frequency of pi by 4 radians per sample. And so if this is pi by 4 minus pi by 4, what this also says is that this signal has a relatively high presence of frequencies around minus pi by 4 to pi by 4. And we talked about earlier that frequencies which are near around 0 in discrete time, they are called low frequencies. So what this means is that this signal has relatively high presence of low frequencies. So this is what the amplitude plot of the DTFT can tell you, whether the signal has high frequencies more in it than low frequencies, and what is the magnitude of them. We are not plotting here the phase. Now, on the other hand, if I were given a signal whose DTFT was like this, minus pi to pi, this is 0, and it looked more like this. Okay. And of course, there's periodic repetition. I'm not drawing that. Now, compared to the above case, what this says is that this signal has more high frequencies. So remember, frequencies around pi or minus pi are the high frequencies. So what this says is that this signal has a relatively high presence of high frequencies, and it does not have that many low frequencies. Okay. So just like the case of the continuous time phenomenon, discrete time Fourier transform effectively helps us understand signals in terms of frequencies, low frequencies, high frequencies, and as we will see later, it helps us essentially say that the job of a discrete time system, just like the job of a continuous time system, LTI system specifically, is nothing more than either kill off frequencies in your input signal, or amplify or damp your input frequencies, or change the phases of your frequencies in the input signal. It doesn't do anything more. Okay, we'll come to that later. So as time goes on, we'll be looking at the discrete time Fourier transform of many important classes of signals. One of the classical examples is, of course, that of the delta function in the discrete time. So this is just example 3.5 in your text, which is xn equal to delta n. Okay. So this is a signal which is 0 everywhere except at 0. And so forth. Now, if you just think of it in terms of an intuitive understanding of what kind of frequencies exist in this signal. And we will do the math later. But think about it. This is a signal that is 0. All of a sudden it becomes 1 and it becomes 0 again. There is no signal in the world that can effectively change faster than this signal. Right? 0 suddenly becomes 1, becomes 0. What it says is that if you intuitively try to think of it, this signal really needs all kinds of frequencies to be present in it. Okay? 0 suddenly becomes 1, becomes 0 again. It must, to recreate that signal, you must have a lot of frequencies present in your signal. Okay? So that's sort of the intuitive understanding, and you can try to now compute it, and I'm sure you can reason from your continuous time world. If you calculate the Fourier transform of xn, which is x of e to the j omega, just use the formula n from minus infinity to infinity, x of n e to the minus j omega n. Now xn is equal to 0 for all n except n equal to 0. So the only summation we are left with is 1 times e to the minus j 0. And what is e to the minus j 0? It is 1. So what does that mean? My DTFT of my impulse function is a constant 1, which means that if I look at its DTFT plot from minus pi to pi and going forward, of course, periodic repetition of a constant is just a constant. What it means is that a unit, this delta function has actually all frequencies present in it. Every possible frequency is present in it, and all the frequencies have the same contribution. Okay, little omega equal to 0 has a contribution, little omega equal to pi has a contribution, and all of these frequencies have a contribution equal to 1. Okay. So since this signal just suddenly changes, you need a lot of frequencies in it. It has low frequencies, it has high frequencies, all sorts of frequencies. And this is very analogous to the continuous time world. If you think of the impulse function, right, delta of t, what's the continuous time Fourier transform of delta of t? It's a constant. Okay. So it's very analogous. You will see again and again, with a few exceptions, that the intuitions that you draw in the continuous time world carry over to the discrete time world. Let's look at another example, which is example 3.6 in your text. So this is an example of what's called a damp exponential. So absolute value of alpha is less than 1. Okay, so it's multiplied with a unit step, which means that it is always 0 before n equal to 0. At n equal to 0, it is 1. Okay, and then after n bigger than 0, if my absolute value is less than 1, here I'm assuming alpha is a real value. It can be complex value too. If my absolute value is less than 1, then what is happening is that this thing is going down. Right? With every passing value, it is decreasing. Okay, so it's a damped exponential. It's going to 0. I want to make sure no one confuses that with a continuous time signal. This is just, I'll often be using an envelope of a discrete time signal. But for example, if alpha was positive valued, you will have a sequence like this. Right? So let's look at what is the Fourier transform of this. Again, you can use the same formula. N from minus infinity to infinity, alpha n un e to the minus j omega n. So everything is 0 for n less than 0. So we just get rid of the unit step go from n equal to 0 to infinity alpha n e to the minus j omega n. And then oftentimes in discrete time Fourier transform calculations, our end goal will be to reduce our summation. These summations are infinite summations. We want to reduce them to a geometric sum. Okay. So n equal to 0 to infinity alpha e to the minus j omega whole n. Right? If we can write it like this, if we remember the geometric sum formula, if we have n equal to 0 to infinity r to the minus 1, then we know that as long as absolute value of r is less than 1, this sum is finite and its value is given by 1 over 1 minus r. Right? So if we apply that formula, r in our case is r equal to alpha e to the minus j omega, and absolute value of r is absolute value of alpha, which we already said is less than 1. So our Fourier transform will be 1 minus alpha e to the minus j omega. Okay. So this is the Fourier transform. This is now a complex valued Fourier transform. It has magnitude. We can compute its magnitude and we can compute its phase. So I'm going to just demonstrate this Fourier transform. I wrote a little function. You can write that in your own case too, which I'm only plotting the first 50 samples. Okay. And this function you pass in the value of alpha, and it basically just plots the magnitude and phase of the Fourier transform. So let's try to reason about these Fourier transforms. So the first example that I did was I took alpha equal to 0.9. Okay, which means this is what the signal looks like. Okay, it's decaying as n goes on. This is x of n. Okay, and as I wrote, my Fourier transform of decaying exponential, which is something that you should memorize or at least have an idea of, it looks like this. So I can now plot its absolute value, which will tell me the different frequencies present in it, and this is what it looks like. Okay, this is the absolute value, and this is the phase of x of e to the j omega. Okay. Again, as you saw and as we have argued, so this is, we have about pi is somewhere here. As you see, the discrete time Fourier transform is periodic. Okay. And what this says is that this signal, this decaying exponential signal, consists of mostly low frequencies. The presence of high frequencies, which are around pi, if you look at this region, they are very close to 0. So this consists of mostly high frequencies, low frequencies. And these are the phases of those frequencies. Okay. Now this plot is a function of your alpha. So what's going to happen? If my alpha is very close to 1, what is happening? My signal is going to 0 very slowly. Intuitively, the closer alpha is to 1, the more slowly my signal is changing. If my signal is changing slowly, then intuitively it should have less high frequencies. On the other hand, if I make alpha small, then it's going to 0 very fast. Right? The closer I make alpha to 0, the faster it's going to go to 0. And because of that, we expect that the Fourier transform of that will have more presence of high frequencies. So let's try to verify that. Let's change our alpha from 0.9 to 0.1. Okay? And if you compare, this is what it looks like. Because it's 0.1, it's rapidly going to 0. It's not never approaching exactly 0. You can zoom in and see some value. But if you compare from alpha equal to 0.9, which is this thing, to alpha equal to 0.1, which is this thing, it's clear that the second signal is going to 0 much faster. So we expect that that signal should have more high frequencies present in it. And if I plot the DTFT of that, indeed, that is what I see. This is pi, and this is minus pi. And if you remember, the previous case, it was going to 0 for frequencies around pi. In this case, this is not really going to 0 up till it reaches pi, which means that it has frequencies which are high frequencies and still present in it. Okay, this is the phase, but we are right now talking about the amplitude. So if you really compare the two, this is the case of slow decaying function, and because of that, it has low frequencies but not that many high frequencies. And this is the high decaying function. Because of that, it has high frequencies also present in it. Okay, and the ultimate of that, if I take alpha equal to, if I take alpha equal to 0, right? If I take alpha absolutely very, very, very close to 0, it's going to look more and more like that impulse function, and the high frequencies will keep on becoming more and more. So what I would encourage is that you basically write up this code and play with different values of alpha to see how does the fluctuations in the signal correspond to the DTFT. Because the goal shouldn't just be that you can write down the formula. The goal should be you can really understand what the DTFT is telling you. So we now understand the DTFT in terms of both its definition and its operational meaning in terms of at least signals. We'll come to the systems, frequency domain interpretation of LTI systems and DTFT later. A few of the properties of DTFT, which are very similar to what you did for the continuous time Fourier transform, we'll study them next. So I want to make sure that we are all on the same page with respect to the notational convention. So there is a meaning of an even function, which is the same in continuous and discrete time. I'm sure you have studied that in the discrete world, but I'll just remind you, an even function is one which is just symmetric around 0. Okay? So whatever the function is doing on the positive valued axis, it's just a mirror reflection of what is happening on the negative valued axis. In the discrete world, for example, this is an even function. Okay? Whatever is happening here is the same what is happening on the negative side. There is a definition of an odd function, which is that xn equal to minus x of minus n, which you can think of it as reflection around the origin. Okay, so by this very token, and all of this even and odd functions are defined for real valued functions or sequences. So by this definition, actually, if you put n equal to 0, then you have x0 equal to minus x0. The only possible explanation for that is an odd function has to have 0 at n equal to 0. So odd functions are always 0 at n equal to 0, and then they are mirror reflection of each other around this origin. Okay, so if this, you can think of it as like this is the reflection axis. Okay, And the idea is that every real valued can be written as a sum of an even and odd function. And here I'm just writing them for the case of discrete time. The same definitions exactly applied for the case of continuous functions. So if you are given a sequence xn or function, you can always write that as an even part x even plus odd part x odd n. And the way to define this is you can define x even n equal to half of xn plus x of minus n, and x odd n is equal to half of xn minus x minus n. Okay, you can verify that this x even n is indeed even, x odd n is indeed odd, and if you add them up, it's trivial to see that it becomes equal to xn. So every real valued function can be written like this. For complex valued functions, the terms are a little different. In complex valued setups, what you have is the terms that are used are conjugate symmetry. So you have conjugate symmetric functions. And the definition of that is that xn equal to x minus n, but also conjugation. Okay? So, and if you all remember that conjugation does not impact the amplitude. What does conjugation do? It just changes the phase. So what it says is that the amplitude of a conjugate symmetric function is even, and its phase basically on the whatever is on the even side, it's the conjugation of it on the whatever is on the positive valued axis, it's conjugation on the negative valued axis. And you have the notion of conjugate anti-symmetric function, which is x of n, again the same definition as odd but with conjugation. Okay. And the same principle applies that any complex valued function can be written as a sum of conjugate symmetric, I'll use CS, and conjugate anti-symmetric functions. So you can write x of n, if it's complex valued, equal to x CSn plus x ACSn, where the definitions are analogous to the even and odd function. It's half of xn plus x conjugate minus n, and x of ACSn is half of xn minus x conjugate of minus n. The reason we are defining these terms is they will be used again and again. They are really helpful in terms of doing many analytical tasks. Okay? We'll learn some few things when we look at symmetry properties based upon this, and sometimes when we are doing analysis, we can really use these to simplify the analysis. So in the next class, what we will go over is very quickly some of the symmetry relationships based upon these properties. And we'll look at then other properties of the discrete time Fourier transforms.